two apologies. First one, I can't speak nearly as fast as Mary, so that I will have to take longer. The other thing is, my original title was CP Manganese Tricarbonyl, where it took me. It has now been changed to where it took us, because Mike George has sent me some slides, which I will show mostly in the middle of the talk. He sent me the slides, but not the jokes, so it may be a bit more serious. And I should begin by explaining why there is an EU flag there, which is particularly unusual from someone from England. And this is because under the second framework programme in the 1980s, there was a project coordinated by me at Nottingham, where there were 3 partners, and the bottom one was the School of Chemistry at the National Institute of Higher Education, which those of you who are older may remember as this institution. And this morning, Conor took me to show me the plaque which commemorated the founding of this naming of this university, and he said that most of you would have no idea where it was. So now you've seen it, and Conor, when he comes back retired, will lead expeditions to look at it. So this is the structure of CP Manganese Tricarbonyl. Most of you probably know that. This is a picture of it. It's quite a nice orange colour. I think that's not a very faithful reproduction of the colour. But the reason why it's unusual, it is an extremely stable metal carbonyl, and it has a very strong metal carbonyl bond, and it has very intense infrared band, so it's really good for infrared spectroscopy. And you cannot displace the CO by heating. Well, I mean, if you heat it to thousands of degrees, it will decompose, but you can't induce thermal reactions, so it's really great for photochemistry. And when we started the project, Dublin, which means John Kelly at Trinity, had UV spectroscopy, and Nottingham had time-resolved infrared. So there was an obvious collaboration in the ways that you've seen in some of the other lectures. And in fact, this grant, this network paid for Conor's first laser and the arrival of flash photolysis here in DCU. And as you know, this time-resolved infrared or spectroscopy is to try and work out what happens in the middle, and you have a UV flash in the infrared cell and the infrared source and electronics. And in the 1980s, everything was much slower, but it was still useful because nobody had ever studied these things before. So some of you may not have seen an infrared laser, so this is the laser. And in fact, the laser is just a tiny bit of that. And this is a standard size strawberry, so you can see the infrared laser is not a very big device, but it can record spectra. And you get spectra like the ones you've seen with most of the day, where you get peaks going down depleted from the starting material and intermediates, and then products growing in. So what happened with CP manganese was we found that there was a two-stage reaction. The light split off carbon monoxide. I made it bigger there, but it's really the same size. And so you get this CP manganese dicarbonyl, and then you get a second reaction. The CP manganese dicarbonyl reacted, and you could tell this from the kinetics, with more starting material to make some product. And so the question was what this product was, and by looking at the infrared, we could see a band just below 1800 wave numbers, which is indicative of a bridging carbonyl band. And if we enrich the product, the starting material, with 13 CO, we got a second band, just one, which indicated that there must be only a single bridging carbonyl. So we postulated in the paper this compound, which you can count up as 5 carbonyl groups, 2 manganese and 2 CP. and it was reasonably stable. And we published a paper where Bernie Creefan is, you can see, the lead author. And at the end it said, we thank the EEC, it was before it was the EU for the grant, which has enabled us to collaborate. And then in the third 6-month report, which I found, it said, Ms. B.S. Creefan, because you were apparently doctor then, visited Mülheim on August the 11th to the 27th to attempt the photochemical synthesis of CP2-Mn2CO5, a species already observed as a transition species in flash photolysis experiments. Unfortunately, these experiments were unsuccessful. The reason for this is lack of success is so far unknown. So, but she got a nice trip to look at. So I now need to admit to a huge mistake that I made. You can imagine, and this may happen to you, the students, if you discover something new, you think it'd be really good to think of a new scientific term. So, in this case, you have this reaction where you're making dimer, and since this is the parent and this is the child, I thought a really good name for this sort of material, I would call it a it had two disadvantages. First of all, you could never put it in print. And secondly, and this is why it was a really bad thing, is for the next 3 or 4 years, every time our students saw a peak that they didn't understand in the spectrum, they just said, oh, it's an incestum. So it was a terrible mistake. And so be warned, if you think of the term, think of the consequences first. So now, let me introduce Mike George. You've seen this photo already. This is a slightly better version, brighter version than John Kelly showed. There's me, and then this is my PhD supervisor. That's why it says -1, one generation back, Jim Turner, who was described that during lunch today as being a true gentleman chemist, which I think is a very nice description. Then this is his supervisor, so my scientific grandfather. And then here is Mike George, who was my scientific son, and Shwejong Sun, who is Mike's PhD student, so my scientific grandchild, so you can see 5. And now the generations continue to +3 and so on. And so these are now Mike's slides. And so you can see it says, collaboration with Conor was my first independent paper. Mine is mine. And this is his paper, and which I think may have already been shown in Mary's talk. And so Mike said, thank you. And, then Mike, well, one of the things Mike has been really interested in is in so-called alkane complexes. And this is something from a journal, an article in Chemistry World, in which says it's a dream of catalytic chemists to break CH bonds, CH activation. And the first stage of this is thought to be complexes in which an alkane with CH bond is bonded to a metal. And so Mike has always dreamed of forming these. And as was hinted in John's talk, if you take something like methyl hexacarbonyl, the thing that Conor started with, when you photolyze this in a solvent, you lose CO, and within a picosecond it's reacted with the solvent, and then you get a slow reaction, which the solvent is displaced by the ligand. I also thought of a term for this, which I call the token ligand, which is perhaps slightly less crude than incestima, which sort of hasn't caught on either. And this, I'm sorry, is a terrible slide because you can't read any of the numbers, but Mike put it in a format in which I couldn't get it any bigger. But what it shows is that he's gone on much of the periodic table. I'm sorry, there isn't a periodic table there, so there's part of one on my time. And so I suppose the nurses don't need a periodic table. And there isn't a clock in here either, but I suppose the nurses each have a little watch. And so the gist was that Mike noticed that the manganese complex, alkane complex, was more stable than the others. So he guessed, because these groups, the alkane complexes that you see by flash photolysis, get more stable as you go down. He guessed that rhenium might be the most stable. And when he did it, he found that the rhenium complex with heptane solution had a lifetime of several microseconds at room temperature. And then a chemist, I can't remember whether he was in New Zealand or Bull in Australia, actually managed at low temperature to record the spectrum of C3 rhenium alkane, and you can see this is an NMR spectrum. I'm not an NMR spectroscopist, so apart from saying, look, they're peaks. But you can see when you go to deuterium